Okay, so from our slackline experiment, we have collected some data. So let's use Bryce, for example. So we knew that the vertical depression on the slackline was 24.5 inches, and the length from his foot to the anchor point was 174 inches, right? And we found out that he weighs 165 pounds. So we have this side length triangle going on, yes? And then over here, we drew a force diagram. So we have the force due to gravity pulling down on Bryce has to be canceled by the line pulling up and out, right? So the ups, we broke off, and we said, okay, each up has to account for half the down, right? Because he's not experiencing acceleration. And these two inside guys have to point in opposite directions, right? That's the outs have to cancel. Otherwise, he'd be thrown to one side. Okay? Which is what would happen if the thing broke. Right? Okay, so to put some numbers to these, what do we know about gravity here? We went and learned that the constant is 32. Yeah, 32 feet per second squared. Okay, so what's gravity then? Gravity is, for Bryce, 165 times 32 is 5,280, and that's pointed in the J direction, right? Okay, so what does that make our vertical component of our little gravity deal? Or our vertical component of the rope vector? Half of that with a minus sign, so that gets to be minus 2640 J's. Note, apparently I put my positive y-axis down like a dummy. Whatever. You get to pick that. I picked wrong, so whatever. Now, what else do I need to know here? What am I looking for? I was looking for how... What?
Force of the tension on the rope.
Yeah, I was looking for the tensions either down the rope or in on the posts. Either of those was interesting to me. You guys cool with that? So in on the posts is going to be these two flat vectors, and on the rope is going to be this blue guy. You guys see that? Okay, so what do I need to do to figure this out? Help. What was the hint I gave you guys? Yeah, you need to figure out what the angle is, right? Okay, so you go over here, and where's the angle theta that I marked in that triangle in this one?
Top right.
Top right. That's an opposite interior angle thing. Or it's right here, yeah? And then if you found this one, you'd take that one and subtract it from 90 to get the other one. However you end up with this. What did you guys get for this angle theta?
8.1. Oh, never mind. That's for doing this wrong. I was did that.
Okay, so from the Bryce side of the room, what'd you get for the angle theta?
0.14 radians.
0.14 rads? How'd you get that? What'd you do?
What did it? See. Oh, inverse sine.
Okay, yeah, so you might look at this and you think to yourself, okay, I know that the sine of theta, right, is the opposite, the side opposite theta divided by the hypotenuse. So this is 24.5 divided by 174, and then we inverse sine both sides, and we find that out. You guys with me on that? Okay, once I know the angle theta, what do I do with that business? Take that, take it out of your side length triangle and put it in your vector triangle. So I know that the angle in here is 0.14. Now I want to know either this guy or that guy, right? How about this guy?
Tangent.
Yeah, that's going to be a tangent, right? So what I know, oh, whoops, no. Okay, so what I know is that tangent of 0.14 radians, right, is the what's tangent got to do again? Opposite over the adjacent. So this side is 2640 long, right? Okay, so my opposite is 2640 long, and my adjacent is, yeah, I have no idea. That's what I'm looking for, right? So let's call that x. So what do you do? Multiply both sides by x, divide both sides by tangent of 0.14, making sure that your calculator's in radians. Get x is 2640 divided by tangent of 0.14, which is, somebody?
18,734 pounds. Pounds feet per second squared.
Yeah, inconvenient units, right? This is pound feet per second times seconds. That's like the imperial analog of newtons, right?
Yeah.
Which is super annoying. I really should have done this problem in metric, right? Because I kind of know what a newton feels like. A newton's like what a water bottle feels like in your hand.
Oh yeah, huh?
Yeah, and that's like, what? I don't know. 16 of these or something? Really aggravating. Okay, so what I found out is that this side, right, is 18,734, and if I wanted to do a good job with labeling, that's a vector, right? So that should be in the which direction? I. And then what's this one on the other side? Yeah, that one's minus 18,734 I. Right, because those two have to cancel out. You guys see that? With me? Okay. How do I know that this is in the ballpark of the right thing?
The numbers look too high to me.
Yeah, the numbers look really big because I'm operating in feet pounds per second. How about this? How does this force compare with that force in magnitude? Like this is what it means to weigh 165 pounds, right? That's what Bryce walks around with every day. 5,280 seems like a big number, right? But it's just what 165 pounds looks like in our gravity well. So how much bigger is this thing, or what's the...
About 3 times as much.
Yeah, it's like 3 and a little bit more times as much. See that? So we're pulling in on the posts, on each post, at about 3.5 times what we're putting on the line. Does that make sense? Yeah, I mean, heck, if this is like an 8-degree angle, right? That side's going to be quite a bit bigger than this side. You guys all see that? How can I get this other tension 2? What's tension 2? Good, we get Pythagorean theorem to find out how big it is. I know what it is right now, though. What's tension 2 right now? It's 18,734 I's, right? And negative 2640 J's. You guys see that? And if I want to know how long it is, I use the Pythagorean theorem using this side length and that side length. What do you guys get if you do that? So what's the magnitude of T2? How long is T2? Anybody Pythagorean theorem me quicker? So what do I need to Pythagorean theorem T2?
18,919.
Does that seem right?
Why do you have 18.734?
That's a comma. Does that seem right?
No.
No, not really. Why doesn't it look right in the picture?
The picture isn't on the scales.
That's supposed to be an 8-degree angle, right? What do I have drawn up here?
45.
Yeah, like 30 or maybe 40 degrees. You guys see that? Is it possible that this is only 200 longer?
Yeah.
Yeah, I mean, you're squaring everything, right? So when I square 18,000, I get a really, really big number, right? When I square 2,600, it's close, but it's not anywhere near that big. When I add those together, the thing that dominates is really this guy. That's really saying, right, when you have a really flat triangle, the hypotenuse is about the horizontal, which is why you guys couldn't get a decent measurement for this thing. Because it really is pretty close to this length. You guys cool with that? Does this process make sense? So should we take the load cell out and see if we can figure out that we got about 3 times the force?